Hey everyone, welcome to the lecture for 12.4. So when we're thinking about correlation between two samples, let's kind of scale it back one more step. Where did those samples come from? Well, we know that samples come from populations. So let's say we have two populations, population X, and we also have population Y. So what we did when we computed our correlation coefficient, we took a sample from both populations. So we took a sample from population X and we took a sample from population Y. And remember, we had to plot them on a graph. So there should be as many data values in our sample from population X as there are in our sample from population Y. So we have equal sample sizes in their both populations. And what we did is we compared these two samples to each other, and we found that there was something called the correlation coefficient. And we denoted that with the symbol R. Right? And so this correlation coefficient, it told us something about how the data was related. So we had the idea of strong, weak, moderate. We had the idea of positive and negative. We had the idea of no correlation. But in as much as we've talked about getting, say, maybe like an X bar from a sample and how that relates to a mu, right, for the population, I hope it doesn't surprise you to know that R is the sample statistic for this for X samples X and Y, and it relates to the parameter rho. So this is the correlation coefficient for the population. Whereas R is the correlation coefficient for the sample. Right, so think about how X bar relates to mu, or think about maybe how S relates to sigma. It's that very same idea between population parameters and sample statistics. So when we get a sample, we might want to ask ourselves, is this indicative of the population parameter? Is this a good sample? Is my correlation coefficient telling me a broader picture about rho, the correlation of the population? And so we address those questions, or we answer those questions using a hypothesis test. So the way that we're going to work the hypothesis test for a correlation coefficient is we're always going to assume that rho is 0. We're always going to assume that the population correlation, well, that there is none, that it's 0. And that's going to be our null hypothesis. So we're going to have H naught is always that rho, and I know it looks a lot like P, so don't worry, that's not lost on me, but it's got a slight slant to it, and it doesn't have a little stick coming out right here. So it's going to be that rho equals 0. So again, you're going to assume no correlation, because remember, when you are conducting a hypothesis test, we never get to affirm the null hypothesis, right? We only get to really test whether or not, like if the alternative hypothesis. And so for us, the alternative hypothesis is that rho is significantly and statistically different from 0. That is, rho is not equal to 0, right? So this is saying that there is some correlation among population X and population Y. And also notice that this is telling us that we have a two-tailed test. So when we do this, what happens is that we're going to use a t-test. We're always going to use a t-test when using correlation. And so our t statistic, or our test statistic, is going to be given by t is equal to r times the square root of n minus 2 divided by the square root of 1 minus r squared. So this is just kind of good to know information, but it's all going to be programmed into Excel. And also, we don't have to worry too much about the degrees of freedom because, again, that's going to be programmed into Excel. So we're going to use n minus 2. So if n is our sample size, then our degrees of freedom is equal to n minus 2. All right, I had to take a quick break to convert this into text. All right, so we have our test statistic t, which means we're using our students' t distribution here. And remember that the test statistic tells us how far away we are from the center of our distribution. And really that's telling us how far away we are from rho equals 0. For a level of significance, if it's not explicitly stated, we're just going to go ahead and use 0.05. And for the sample size, this is going to be the size of each sample. So let's go back up to the top really quickly. Notice that we took a sample of size n from population X, and we took a sample from size n of population Y. So the sample size that we're going to input into Excel is going to be n. It's not the sum of all the data, which would be 2n. It's just the size of each sample. And remember that they have to match in order to compute a correlation coefficient. And as before, we're also going to consider the p-value. So if p, and again, this is not rho, and I understand they look similar, but if p is less than alpha, then we're going to reject the claim that there is no correlation between the data. So rejecting that claim is actually really saying that, well, in fact, we do think there is correlation between the data. And this is going to allow us to use R, our correlation coefficient, as a predictive tool later on. This is kind of the first step in being allowed to use R as a predictive tool. If rho is greater than alpha, then we're going to fail to reject the claim that there is no correlation. And in this case, we wouldn't be allowed to use R as a predictive tool because we haven't shown sufficient evidence to demonstrate that there is correlation, or a lack of no correlation rather. So let's see if we can use this example here. Suppose we computed a correlation coefficient of a sample where we got R equals 0.801, and we had a sample size of 10. We want to test this at the 10% significance level. Can we justify that correlation exists among the populations? Well, let's go to Excel and see what it says. So when we go to Excel, we'll notice that we don't have the opportunity to type in a value for rho. And that is because when we are doing a hypothesis test for correlation, we always assume that rho is 0. We always assume that there is no correlation among the populations, because what we want to test, what we want to show is that there is. So that's our our alternative hypothesis. And so those are kind of fixed. We never have to fuss with those. So it's always is good practice to state your null and alternative hypotheses. So here, of course, H naught, rho is 0. HA, rho is not 0. And so that means we're always going to have this two-tailed test. The problem tells us what our level of significance is. It says it's 10%. So I'm going to use 0.10, And I'm going to go ahead and type that in for alpha in my sheet. So 0.10. And then for my sample size, this is telling me that we used a sample size of 10. So I'm also going to enter that into my Excel sheet. And it also is telling me that we computed R to be 0.801. So when I compute this, it's telling me my test statistic. So my test statistic ended up being 3.78437. So that's really telling me that I am 3.78437 standard deviations away from the center here at 0. And so that's quite a bit. So let's paste this into OneNote and kind of examine it further. So here I can see that my value for my sample correlation was 0.801. And so that was 3.78437 standard deviations away from the assumed value for rho. So remember, this tells us how far away we are. So if I were to kind of mark off where everything is, here's rho equals 0. And because my test statistic is positive, it's telling me that I'm to the right, 3.78437 standard deviations above rho equals 0. Moreover, it's telling me that the probability of being that far out is 0.00535. So this is telling me that the probability of being at least this far away, and by this far, I'm talking about 3.78437 standard deviations or more, from the center where rho equals 0. The probability of that is very small. It's 0.00535 or 0.535%. So that's quite small. Now let's look at what that really means. So it's just talking about the area on these two tails, right? I think my graph isn't really doing me any justice here because it's cutting off. But so you can imagine that you're at these two tails. And so what we have is that the rejection region because alpha is 0.1, the rejection region is really like 5% on each side, right? And so certainly our sample correlation R fell within the rejection region. And one way we could think about this, or the other way we can think about this is, well, is P, again, not rho, is P less than or equal to alpha? Yes, it is. P is 0.00535. It's less than or equal to alpha, which is 0.10. So we are going to reject the claim. that there is no correlation between the two populations. Right? So we're really rejecting the claim that rho equals 0. And so this is going to allow us to use our sample correlation value R as a predictive tool.